Hello, my name is Randall Law from the University of Wisconsin-Madison, and today I'm going to present my observations on the manufacture and raw material provenience of Indus Civilization seals. Indus craftspeople used many types of raw material to make seals. Some of the less common seal materials include silver, faience, kaolinite, serpentine, ivory, and shell. The large majority, however, were carved from steatite, which is the massive form of the mineral talc. The carved seals were then heated and/or given an applied surface treatment in order to lighten or whiten their exterior surfaces. In broken or worn seals, you can often see the unmodified steatite just below the surface. This particular seal from Dholavira is broken in half. And when you look at it in section, you can see quite clearly the dark steatite from which it was carved and the thin veneer of the surface treatment. Here are some images taken at a steatite mine in Baluchistan. You can see that the raw material, even over a small area, is highly variable visually. Also variable is the geologic origin of steatite. Steatite is a rock composed primarily of the mineral talc. It may form in either ultramafic igneous rock formations, such as ophiolite sequences, or dolomitic rock formations. Although the rock formations from which it comes can be very different, the result can be visually identical steatite. Here are two examples from completely different types of parent rock. Ultimately, this causes steatite to have very different trace element characteristics that reflect their respective parent rock formations. And it is these variable trace element characteristics that make sourcing steatite artifacts possible. The very first step in such a study is to locate and acquire samples from as many potential sources as possible. The Indus Civilization encompassed a huge swath of northwestern South Asia. But over the space of about 3 years, from 2000 to roughly 2003, I was able to visit many potential source areas and, with some help, acquire the steatite samples that I needed. Ultimately, samples from 38 individual steatite sources, both dolomitic and ultramafic in origin, were collected and included in the geologic sample database. Instrumental neutron activation analysis of both geologic samples and steatite artifacts took place at the University of Wisconsin-Madison's Nuclear Reactor Laboratory under the direction of Lab Director Robert Agassi. Neutron activation is a powerful and precise method with which to determine the trace element composition of materials. It is also very expensive. And it is at this point that I'd like to acknowledge and thank the many groups, foundations, and institutions that have generously supported this research over the past 2 decades or more. First and foremost among these, the Harappa Archaeological Research Project, as well as the many others listed here. Back to the steatite study. To date, 475 samples from 38 individual steatite sources surrounding the Indus Valley have been analyzed using instrumental neutron activation analysis. The resulting data were evaluated using canonical discriminant analysis, which produces maximum statistical separation between the individual sources. All of the geologic source samples are being compared here. The samples from dolomitic sources are shown in green, and the samples from ultramafic sources are shown in black and white. There's a distinct separation between the two groups, with ultramafic sources being differentiated by their high levels of transition metals, and the dolomitic sources being moved off to the left hand of this chart, mainly due to their higher concentrations of rare earth elements. To date, over 230 steatite artifacts representing 10 Indus Civilization sites have been analyzed. Here they are compared to the full geologic database, and you can immediately see that the vast majority of them cluster quite closely with geologic samples from sources of dolomitic origin. Only a handful fall with ultramafic sources. Many further iterations of canonical discriminant analysis were conducted. However, time does not permit me to show them all here. Basically, what was done is that we gradually pared down the number of source groups in the database to focus individual steatite artifacts on the particular source that they were most likely to come from. In the end, we were able to get a predicted group or a predicted source membership for each individual artifact. And based on that, we have produced a provisional map of steatite acquisition networks in the ancient Indus Civilization. Over 95% of the 140 steatite artifacts analyzed from the site of Harappa came from dolomitic sources located north of the Indus Basin. The majority of these were from the Hazara area, but some also came from other sources in the Khyber Pakhtunkhwa region as well as Jammu. Steatite artifacts from 9 additional Indus Civilization sites have been analyzed. The large majority of steatite artifacts analyzed from the Indus cities of Mohenjo-daro, Rakhigarhi, and Dholavira seem also to have come from the same northern sources utilized by craftspeople at Harappa. A small amount of steatite from other, comparatively close by regional sources is present at several of the Indus sites that have been studied. For example, steatite from Baluchistan was found at the site of Neutron, and steatite from southern Rajasthan was found at several sites in Gujarat. And some of this material from alternate sources was even transported as far away as Mohenjo-daro and Harappa, but only in very limited amounts. In the end, however, it has gradually become clear that the primary Indus steatite trade route ran north to south from the dolomitic sources in the far northern part of Pakistan and northern India, south all the way as far as Gujarat. I need to come clean about one thing. Although this is presented as a geologic provenience study of Indus seals, I've actually analyzed very few seals. Most of the steatite artifacts included in this study are examples of steatite manufacturing debris, which is shown here on the left. Now, one reason that I haven't studied many seals directly themselves should be quite obvious. I can't be cutting or drilling or knocking off pieces of such important and precious artifacts indiscriminately. Another reason is that the optimal sample weight for instrumental neutron activation analysis is 200 milligrams, which is actually quite a lot of material. There were instances where I was able to carefully drill that amount of material from a seal, or in this case, a broken seal blank from Harappa, and thereby analyze a seal directly. Here's an example from the site of Mittal. I was with Tejas Garge and VN Prabhakar, and Tejas found a small seal on the surface. I was permitted to take a little sample of this for analysis, but it was not near enough to meet the 200 milligram standard requirement. The results suggested that it was from northern Rajasthan, but I was always doubtful of this result for a number of reasons, but mainly because it was such a small material sample size. Now, jump forward about 10 years. I'm working with Brad Chase on a new project in which we're analyzing low-weight steatite beads. We can now analyze samples as small as 20 milligrams. This allows me to go back and have the Mittal sample reanalyzed. It also permits me to analyze previously unanalyzable, very tiny seal fragments, such as this one from Rakigare provided by Ayumu Konosakawa and Vasant Shinde, and a fragment of the Shikarpur Rhino seal provided by Professor Ajithprasad. The results of the analysis and reanalysis indicated that all three seals were carved from steatite originating in dolomitic deposits in northern Pakistan. So, what was it, or what is it about steatite in northern Pakistan that made it sought-after material for Indus craftsmen for making seals? Although not universal, one of the most common features of Indus seals is their lightened or white exterior. Experimental studies of steatite debris of all colors from Harappa indicated that after being heated to 1200 degrees Celsius for 1 hour, all examples turned white. But not all steatite turns white. Here I took samples, I carved tablets from 20 different sources, heated them experimentally, and I found that in fact, very few of them turned white. In fact, the ones that did turn white were invariably from sources in northern Pakistan. So I would argue that the reason craftspeople throughout the Indus civilization preferred steatite from sources in northern Pakistan is simply because it fired white. One issue that always intrigued me, however, was the thin veneer on certain seals. Some seals, like the one here on the left, has been fired all the way through, heated all the way through, and it's white all through its section. Others seem to have this thin veneer on it. Why would they do that? Why would Harappan craftspeople do this when they, presumably, if they had white firing steatite, they could simply just fire? Why go to the trouble of making a veneer? It is my feeling that a seal heated all the way through to the core may be more apt to crack or develop cracks in the process, while a seal given a surface veneer would remain intact and have its soft interior protected. Now, I can't prove that either was true, but I do find the veneer itself quite interesting, and I do have some thoughts on how it was produced. Over the years, I've been fortunate enough to conduct a great number of experimental heating studies involving steatite with Professor Mark Knoyer and Dr. Greg Jameson. Over the years, both together and separately, we've cut, carved, bleached, glazed, baked, and x-rayed thousands of samples. We know a great deal about the thermal decomposition of talc, which becomes enstatite when heated to temperatures between 800 and 900 degrees Celsius. Heat it further towards 1100 degrees Celsius, and you get the formation of cristobalite along with enstatite. We know that at these temperatures, it takes only a matter of minutes for an experimentally heated piece of steatite to be fired through and through. This fact and the presence of these high-temperature minerals gives us important clues on the technology behind the manufacture of veneered seal surfaces, like the one found on this seal boss fragment from Harappa. Here is a reconstruction of how it likely appeared when intact. In the photograph of its section, you can see the glazed surface, a glazed crack where it has broken, and the heated and unheated raw material directly beneath the surface. Mineralogical identification using X-ray diffraction analysis was conducted at several points on the seal's exterior and interior areas. A fragment was taken of the veneer itself. Here, an analysis was done on the surface, and the fragment was flipped over and done directly beneath the veneer. The surface was found to be enstatite and cristobalite with a minor amount of talc. Directly beneath that, it was enstatite and talc with a minor amount of cristobalite. Two points were taken on the interior. The discolored area here, probably discolored due to the slight heating of the surface, and the original unheated interior of the stone. In both cases, the X-ray diffraction analysis indicated that this was talc. So this area has been slightly heated, but not enough to convert it to enstatite, which suggests that this was heated for only a brief period of time just to get the exterior veneer to adhere to the body of the talc itself. VPSEM with energy dispersive scans were also conducted on the sample at 2 points: the surface veneer and a small crack where the applied veneer bled into during manufacture. In this backscatter electron image, the surface layer here is quite distinct from the underlying area of solid steatite. You can notice the loose platy structure. This is the enstatite cristobalite that is adhering to the surface of the carved seal. EDS points were taken at 3 different locations, and in each one the material is simply recorded as magnesium silicate, which it would be if it was just enstatite cristobalite. A bit further down on the seal boss section, we have the BSC image of the crack that I mentioned before. And you can see the white material, which is a remnant of the surface veneer that has leaked into this crack during manufacture. An EDS scan was taken at this point, and it revealed that this phase is rich in calcium phosphate. Now, calcium phosphate could just be bone ash, but it also has applications as a colorant. So it's possible that it is part of the slurry or whatever mixture mixed with enstatite cristobalite was applied to the surface of the seal. Attempting to whiten the surface of experimental blocks of steatite has actually been kind of my pastime for the last 20 years or so. And to this point, I haven't been successful. However, I have yet to try a mixture of enstatite, cristobalite, and calcium phosphate slip. We'll see if that works. Based on my observations of the seal boss and other samples from Dholavira, it's a possibility. I hope to conduct new experiments with Professor Mark Knoyer in the coming year. Thank you all very much, and thanks to Mark Knoyer for organizing this impressive symposium.